All right, welcome YouTube. So our third speaker and sort of featured speaker today is Katherine E. Stange, who is an associate professor of mathematics at the University of Colorado Boulder. Broadly speaking, she works in the areas of number theory and arithmetic geometry with research spanning Kleinian groups, abelian varieties, cryptography, arithmetic dynamics, and mathematical illustration. She's earned wide recognition, including being recently elected as a fellow of the Association for Women in Mathematics. And this past summer, her video, Rethinking the Reals on YouTube, won this year's Summer of Math exposition, which, if you don't know, is a spectacular content creation contest started by YouTuber 3Blue1Brown, aimed at fostering the creation of excellent math content online. Some of the most amazing videos I've ever seen are in that competition, and it's really cool that Kate won. And you should watch her video, Rethinking the Reals, if you want to see what it's all about. So I'm really excited to have our speaker today, Katherine Stange. So I will hand the floor to you. I think you might still be muted.
There we go. All right. Are the various technological things working?
Looks good to
Yes,
me.
I think so, yes.
Okay. And you can still hear me? I feel like it muted me by, okay. All right. Well, thank you so much for the introduction. I'm sure this talk can't live up to the generous introduction. So this is an unusual talk for me because I'm trying to talk a little bit about the process of research, about sort of the story and my own personal experiences instead of just the mathematics. But if nothing else, there will be many, many pictures. So I'm going to tell sort of a few different stories of my experiences in research and working on research projects that involved illustration in some way. And the role of the illustration sort of varied in some of these different projects. And so hopefully there's some sort of interesting takeaways. Okay, so let's see if I'm working on slides here. Yep, okay, here. So Ray Bradbury, life is trying things to see if they work. So this first topic that I want to talk about is in the spirit of experimentation. And so the topic is about Apollonian circle packing. So I have to first tell you what an Apollonian circle packing is. So what you do is you take three circles, which are mutually tangent to one another, like in the picture here. And an ancient question of Apollonius was, given three objects, when are there certain other objects which are tangent? And one of the specific cases was this question about circles. Given three circles, what other circles could you add to this which are tangent to the original three? And there's two ways to do this. Those are the two solutions to Apollonius's problem in this situation. And now you have five circles, and so you've got maybe new triples to which you can apply this question and new circles that you can add in. And what it really means doing is adding in new circles into each of these sort of curvilinear triangles that are created in between the circles. And so if you do this forever, then you get this fractal picture, which is called an Apollonian circle packing. Okay, so this is definitely a pretty picture. As a number theorist, I got interested in these. Well, I'll tell you the story about how I came across them a little bit later in the talk, but because of their arithmetic properties. And so there are certain Apollonian circle packings where the curvatures, and the curvature is 1 over the radius, are all integers. So here's an example where I've labeled each circle by its curvature. So radius 1 over 11, radius 1 over 16, the outer one has radius 1 over 6. And so this is kind of surprising and beautiful that you can get the entire packing consisting of integer curvatures. And then as a number theorist, you want to ask, what integers are we actually getting? So the reason that we get integer curvatures is because if you have a Descartes quadruple, 4 mutually tangent circles, and they have curvatures A, B, C, D, then they satisfy this quadratic equation. So this is actually a result due to Descartes and Princess Elizabeth of Bohemia in correspondence. They worked out. It's not an easy thing to prove, but you can prove it with elementary geometry, that the 4 curvatures will satisfy this quadratic relationship. And so in particular, you can see Apollonius's problem inside here, because if you fix 3 of these circles, A, B, and C, then there are 2 possibilities, 2 solutions for D. There's some D and D prime. And in fact, from the quadratic equation, you can derive that D plus D prime is just twice the sum of the original 3 circles. Okay, so that means that if you get to the point in building your packing where you've put together 4 curvatures which are integral, then everything in the whole packing is going to be integral. So it comes down to not an easy, but an elementary geometric observation that you get this behavior. So number theorists want to know if there's some collection of integers which occurs in some natural way, then what integers are we actually getting? All right, so let's explore a little bit. So here's the curvatures mod 5. So I've colored them by the residue class mod 5, and there are 5 colors. I'm sure some of you are counting them. Now here's mod 3. And you can see here that there's only 2 residue classes. So you can only get things which are 0 or 2 mod 3. You can never get anything which is 1 mod 3 in the whole packing. So there does seem to be some sort of restriction modulo certain moduli curvatures which can't appear. On the other hand, there are quite a lot of circles. So at the beginning, you can see that there isn't room to have like 1, 2, 3, 4, 5, 6, 7, 8, 9 in this packing. There's not room for circles that are that big. But in fact, once you start going into the cracks, there's lots of room. So you can count the number of circles whose curvature is below a particular bound. And this actually depends just on the Hausdorff dimension of the fractal. It doesn't matter which Apollonian circle packing you're talking about. The Hausdorff dimension is always the same because you can move these from one to another by Mobius transformations. And so if you want to count the number of curvatures in an integral or a not integral packing, that are below size x, it'll grow like a constant times x to that Hausdorff dimension. And that Hausdorff dimension is a little bigger than 1. And so in particular, if you have an integral Apollonian circle packing, you have to be labeling all of these circles with integers. And so you're going to have repeats because the number of circles is growing too fast. So essentially what you expect is that the multiplicities on average are going to be around x to the 0.3. Okay, so that means there's lots and lots of circles once you go far enough. So you'd kind of expect to get lots and lots of integers. And the question is kind of, are these integers somehow, or is the Apollonian circle packing somehow conspiring against you to skip some integers despite the fact that there's so much room for integers? And the answer is, well, okay, they're definitely skipping some because of this modulus restriction that we saw. But are they skipping any others? That's the question. Okay. So that's what's called the local to global conjecture, and this goes back about 20 years. And Graham, Ligarius, Malles, Wilkes, and Jan wrote a nice series of papers about this, about Apollonian circle packings, about early 2000s. And they made this conjecture, and then Fuchs and Sandin did some data, which I'll show you, and they refined this a little bit. And what the conjecture says is that the congruence restriction can always be described mod 24. The only modulus you have to worry about is 24. That's why we could have something mod 3, but we didn't see anything mod 5. And so what it says is that all of these sufficiently large integers that satisfy the congruence condition, that pass that test, will appear in the packing. Okay, so there's some small ones missing, finitely many, and then there's the congruence restriction. Otherwise, everything should appear. And so this has been interesting to number theorists because it's an example of an orbit of a thin group. And so if you take an orbit of an algebraic group, then the collection of values in the orbit, maybe it's an orbit of vectors in some vector space, and you're looking at the entries of your vectors, say, as a collection of numbers, then you can look at those as a Diophantine question, as a question of what numbers satisfy certain polynomial equations. But thin groups are sort of pieces inside of algebraic groups which are too small to get a handle on in that way, by an algebraic condition. And so figuring out what curvatures appear is sort of a new frontier here. We're developing new tools to prove results in this direction. And so Graham, Ligarius, Malles, Wilkes, and Jan, they proved a certain lower bound for this. Eventually, Bourgain and Fuchs showed that you get positive density amongst the allowable ones by the congruence condition. And Bourgain and Kantorovich showed that you get density 1. So the number of missing curvatures grows more slowly than the curvature bound. But, and then I list myself also because we generalized to some other circle packings. But the conjecture remained open. So the computational evidence that was collected for this. So I wanted to talk about, how do we believe a conjecture, right? How do we believe that this is true? Well, there's the mathematics. There's asking the question of, do we see something that's happening in the mathematics that we expect to sort of, like I said, conspire against something like this happening? And in number theory, a lot of these conjectures are sort of based on a probabilistic approach. You say, okay, well, we know some good reasons why certain things are forced to happen, and otherwise we kind of expect the primes to behave randomly. We expect the integers to behave randomly. And so why shouldn't we get all integers eventually here? If there's room for them and they're popping up sort of at random as you go to your new circles. So there's that heuristic reason to believe. But then there's also the question of data. And so Fuchs and Sanden computed, this is about 10 years ago, so they computed up to about 10 to the 8. So curvatures up to size 10 to the 8 for 2 integral Apollonian circle packings. And so one of them, the top one there, -1, 2, 2, 3, they called the bug eye packing. This picture is from their paper. And this histogram that you see at the right is for that packing. And what they do is they ask, okay, so we saw that the number of curvatures that you expect for the multiplicity that you expect, number of circles for a fixed curvature. So the multiplicity of a particular integer in the packing should be increasing on average. And so what they did is they took a window of curvatures in a certain size. So I don't know if you can see my mouse, but that's right there. And around in the curvatures about this size, you expect on average for an integer to appear around 400 times. So if an integer appears 400 times, you put it in the 400 bin here, and this is a histogram. And you can see this nice, not really bell curve, but something looking kind of probabilistic in some way, right? With an average where you expect. And as you increase that window that you're looking at, this hump will sort of move off to the right. And what we're asking about in the local to global conjecture is if at 0 you actually ever have anything that stays there, or if this drops and you never have any more integers of multiplicity 0, integers which actually don't appear. Okay, so this looks like some good data. I like this way of approaching the data as evidence for this. Okay, so this is just language. So curvature is missing if it's sort of allowed mod 24, but it doesn't actually appear in the packing. Okay, so the missing curvatures for these guys, they computed up to around 10 to the 8, 5 times 10 to the 8, and there was still a small number in that second packing, but those are bigger integers. That's a packing with bigger integers in general, and so maybe we just hadn't gone far enough. And in fact, here's an example of data. This is for a slightly different packing, but this is like what you might look at if you're looking at the data. And, this is sort of traditionally what you do with data, right? You put it on the screen and you look at it, and these are the missing curvatures. And so I don't know, maybe this audience has ideas about what if any pattern might be appearing in these. But if you just look at these, you're like, okay, well, they're getting sparser. Okay, right? Okay, but how else might you explore the data? So we weren't actually trying to attack this question, but we had, with my postdoc, we ran an RU this summer, and we were interested in if you fix a pair of curvatures, then what packings contain those? So we sort of turned the problem around. Instead of asking, here's a packing, what are the curvatures in there? We took, James actually had a previous paper about the Apollonian staircase. It's quite a nice paper where he looked at, if you pick a packing, what curvatures contain it and how deep does it lie within those? And so we kind of wanted to generalize that. So we had a pair of curvatures, and we were going to look at what packings contained those. And so we had 2 students, Summer Haig and Clyde Kurtzer, who were interested in this over the summer. And the idea was just, let's explore, let's try to collect some data. So maybe we can do a little better than just listing out the numbers, right? We can draw a plot. So what we did is we took, like, the X and Y axis are curvatures. So a pair is a position on this plot, pair of curvatures. And then we just looked to see if there actually was some integral Apollonian circle packing which contained that pair of curvatures or not. So we put a black dot if we couldn't find a pair. Those are the ones that those 2 curvatures somehow couldn't exist in the same packing. They maybe repelled each other. Okay. And if the local to global conjecture is true, then in particular, like if you fix one of these curvatures and you look at the things that it repels, it can only be finitely many things. So on any row or column in this plot, you should see finitely many black dots. Okay. All right, so here's an example. This is the actual, this was not made pretty for publication. This was the actual screenshot of what we were looking at. And here's a zoom up on the right, and the squares, because it was resampled, don't even like those are individual dots, even though they're like different shaped rectangles. The labeling on the axes is a little bit mysterious. The color bar is not actually useful, but what you see is kind of what you'd expect, some sparse dots. And we were going to ask some questions about those dots. How many of them are there? Is there any pattern to where they lie? Those kinds of things. So there were lots of different, we kind of broke the graphs up by congruence class, mod 24, because there's different behaviors for those different congruence classes. And so there were actually lots of these graphs for all these like different pairs of congruence classes. And they all looked pretty much like this, except for one of them, which looked like this. And so when we first saw this, we realized, okay, either there's a bug in the program, this pattern is a small numbers pattern that's going to peter out, or the local global conjecture is false. And so we looked for a bug in the program. We ran the data as far as we could, and this pattern doesn't break. You can see these lines on the screen, and there's like not even a single missing black dot out of the pattern as your eye follows it. So it turns out that the local to global conjecture is actually false. And this is how we stumbled on it. So this is sort of a lesson in the way that the exploration and experiment and just playing with things brings you to things that you weren't expecting, right? All the serendipity. So here's another way. This isn't how we discovered it, but I think this is a nice illustration of how we could have discovered it. Because in fact, the pattern that we were picking up in that sort of roundabout way in those graphs that I just showed you was actually already present in the data that had been collected even up to 10 to the 8. So here's a picture. This is a graph of the first 4,000 missing curvatures in a particular packing. So just a reminder, right? We want to know if there's any pattern to these things to try to understand if they're just going to peter out, or if there are families somehow living in here of things that are always missing. And so looking at this, to keep it smaller, you might look at the successive differences between your curvatures. And that gives you a sense of the growth, right? You can see amongst the first 4,000 curvatures that they're getting more and more spaced out. But your eye can also see that this looks like a random spread of things, right? There's no particular pattern to the spacings between these curvatures. They look like they're just sort of coming willy-nilly according to some random process. All right, but suppose you zoom out this picture. So this is up to 4,000 curvatures, and now this one goes up to 10,000. And so you can see that, in fact, the randomness at the beginning, you can still see the graph up to 4,000, the left half of this slide, right? That randomness peters out. It does. And what's left is something patternful. And in fact, what's left is a quadratic family. And because it's a quadratic family, the successive differences will be linear. And that's why this looks like a straight line here. It's in fact several quadratic families. They're interfering with each other, which actually makes the graph even more striking because of these lines. All right. And so this is just an example of how you can really harness your visual system, right? Like the decimal expansion of integers doesn't mean anything to our brains, right? So when we looked at the data, there's a list of missing curvatures, it doesn't mean anything to our brains. But in fact, that data that I had up before on the screen, we went back to it afterwards and realized that the last half of those missing curvatures and just that list of numbers were all 18 times the square. And we just couldn't see it, right? You just can't see that from the decimal expansion, but you can see it from an appropriate picture. Okay, so the conjecture is false. That's kind of the end of this story here, which is, this is an example theorem. We actually classified all of the different ones and stuff, but I won't go into the details. What's kind of interesting about it, though, is that even the proof relies on our geometric intuition. So it turns out that to understand the packings, you naturally, because there's a geometric interpretation of it, you look for families and patterns and stuff. And so it's natural to like fix one curvature and think about the curvatures that are tangent to it within the packing. And that's what this blue family is in the picture on the screen. All the things tangent to that circle of curvature 11. And those things actually take the values of a quadratic form. And that tells you something about the subgroup of the Apollonian group, which controls the symmetries of the picture. And you might not have thought to look at that group unless you had the geometric picture, I feel like. But it turns out that most of the results in this direction rely on understanding these families of quadratic forms, as does this these families of missing curvatures that we discovered. So this packing here has no square curvatures, and the outline of the proof is that you look at this family and you show there can't be any squares in that family. And then you have to say, okay, now let's move to the next family by taking a tangent circle. So maybe I go from the circle of curvature 11 up to that one of 15 and look at the family attached to 15. And that moving by a tangency turns out to be about quadratic reciprocity. So for those number theorists out there, I think this is a beautiful like instance of quadratic reciprocity doing something. Quadratic reciprocity, I would say sort of philosophically, is beyond congruence restrictions. Is the next way in which primes and numbers conspire against you or with you, depending on your perspective. And so the fact that these unknown new families of missing curvatures come from quadratic reciprocity is very satisfying. Okay, so that was mostly about experimentation, but I want to go further into the pictures a bit more. All right, so here's Nietzsche. I don't know how you say his name properly. A man's maturity consists in having found again the seriousness one had as a child at play. I think this resonates with me as a mathematician a lot because, you know, that's what we do as our jobs, right? We somehow manage to get a job where we are paid to just sit around and play with mathematics. Okay, so let's play a sort of game. So this is called an abelian sand pile. All right, so what it is it's a model of sand spreading out across a table. Okay, so I have 16 sand grains precariously balanced in a tower at the origin, and I have a z-squared grid of positions at which sand can lie. So what I'm going to do is I'm going to let the sand topple. If I have at least 4 grains, I'm going to send 1 to each neighbor in my grid. So at 16, I topple 4 to the sides, but I still have more than 4 at the middle, so I topple again. Now I still have more at the middle, so I topple again. Now I still have more at the middle, so I topple again. And now the adjacent sites actually have enough to trigger toppling themselves, so they will each topple. And now some of them sent their grains back to the middle, which can now topple 1 more time. Okay, so that's the game. It's like you start with a tower of sand and you let it flow outwards. All right. So this was, I mean, originally inspired, I think, by physics. I mean, it's not a very realistic model of sand in certain ways, but maybe in other ways it is. And so, but there's an integrality to this. There's definitely some number theory hiding in here somewhere, right? Because we have only, you know, integral grains of sand and integral positions at which they can sit. So here's a picture of what happens if you start with 1,000 grains at the middle. Now, what I've done is I've colored, you know, a position stops toppling if it has 0, 1, 2, or 3 grains of sand at it. If it has more, it will topple more. It can't ever get negative. So there's 4 colors in this picture, supposedly. Okay. And so they represent the number of grains of sand left at each of the positions after you have toppled down until you're mostly flat circle of sand. All right, so if we go to 10,000 grains, we get something that looks like this. If we go to 100,000 grains, we get something that looks like this. 150,000, 250,000. And you can kind of see it looks as if it's almost converging to something, even though what I'm doing is I'm rescaling down to fit the picture on the screen each time. And in each of these sort of regions, especially around near the outside, in each of these sort of regions, you can see what look like kind of regular patterns. Here's a zoom up. Oh, I did 500,000 grains. Okay, now here's a zoom up. And you can see inside here these sort of triangular regions that have these repeating patterns in them. And so you get great complexity from a very simple pattern. It's something like, you know, automata, a game of life, these situations where a simple set of rules gives you beautiful complexity. There's definitely lots going on here that maybe we could try to explain. And so this model was originally proposed by Bach, Tang, and Wiesenfeld as an example of self-organized criticality, which is this idea that somehow you can get this complex behavior out of a simple system. And related to this, Levine, Pegden, and Smart were interested in trying to describe exactly what's going on inside this picture. And they were looking at these regions that had repeating patterns, and they found that each one of them was sort of associated to a quadratic function that controls the number of topplings. So I'm not going to go into the details here, but I'm going to say that basically they have these matrices, which they called integer superharmonic matrices. These are 2x2 matrices representing quadratic forms. And each one of those represents some sand, which you topple and will eventually give you a beautiful periodic pattern. Okay. So then they figured, okay, so when does this pattern stabilize into a nice pattern and when does it not? I'm not giving it the details here because I have to skip over it to get where I'm going. But basically they had quadratic forms from which you get some patterns that, you know, sort of seem to be stable or not stable. And they figured, okay, in this sort of three-dimensional space of quadratic forms, there's some region where they're stable and some region where they're not. So they tried to graph this, like just went to the computer to take a look at what this region looked like. And here is the picture. So they expected it to be like the ones low down in their parameterization of the space would have the stability property and the ones above wouldn't, but they did not expect this beautiful fractal shape to the surface between the two parts of the parameter space. And if you look carefully at this, in fact, it's an Apollonian circle packing again. So this is actually how I found out about Apollonian circle packings, was that Lionel Levine, whom I'd known for many years, he called me up because I was a known number theorist to him and said, what do you know about Apollonian circle packings? And I said, absolutely nothing, but there's a talk about them next week, so I'll go to that. And so I learned about these because of that. So here's a sort of schematic which shows that each of these cones is really a circle in the Apollonian circle packing, and it's associated to some sort of lattice. And at this point, I mean, it's actually kind of good I hid all the details for you in the last slide or two, because that's where I was in terms of the research, right? I didn't know anything about what they were doing, where this was coming from. They just sent me a Apollonian circle packing where you could look at the circles and it would give you a repeating pattern. That's it. It's basically the data that's on the screen. It's like you have in fact, it was even less than that. They only told me the periodicity, not the exact picture of the pattern. So actually it looked like, oh, I just wanted to point out that these are the patterns from the regions here. So you see them again. They sent it to me. It was actually like a website where you could scroll your mouse over a particular circle and it would tell you a basis, some random basis for the lattice of periodicity of the corresponding pattern. So I didn't know anything about where this was coming from. I just knew that for each circle in the Apollonian circle packing, there was a lattice. Now, everything I learned about Apollonian circle packings, for each circle, there was a curvature. And it turned out that the curvature was the covolume of the lattice. And I knew that the curvatures had this recursive structure given by Descartes' formula, where you can relate the curvatures of nearby circles to one another. So maybe these lattices would relate to each other in some way. But it was basically just this like website where I could mouse over and look at stuff and write down the lattice and then like try to guess what was going on. But I found it so intriguing because there's clearly some important pattern going on there, but it's so mysterious what it is. Okay, so that's where I learned about Apollonian circle packings. And at the time, it actually reminded me of Conway's topograph, which I won't talk about today, but I want to encourage everybody to go and learn about. Conway's topograph, which is in the upper left on this slide here, is a way of describing the values of a quadratic form in a geometric arrangement. So it's basically an infinite tree. You can just see the beginning of it there. And then the values of the form at various points you can place into the regions that the tree delineates. There I've actually labeled it with the rationals. It's also sort of a picture of the rational numbers in some way, organized in a natural way. So I'm not going to dive into it, but somehow these lattices reminded me of that. And I went deep into this sort of combinatorial rabbit hole of figuring out how instead of quadratic forms, it was really a story about Hermitian forms. And this tetrahedron here somehow represents 4 circles which are tangent to each other. So the edges are the tangencies, and then these are values of the forms that label the parts of the tetrahedron. I mean, I'm not going to go into this story, but it all came from this this experimental approach. I mean, none of this would have gotten discovered if they hadn't graphed that set of matrices to begin with. They had no expectation that it would have all of this beautiful symmetry. So yeah, so I mean, one thing to mention maybe is that, you know, whenever you see these pictures, I think when you see a picture with symmetry, you know that there's some underlying group going on, and your visual system is extremely well designed to pick up patterns and to pick up symmetries. And sometimes when you don't know to even expect that there's some sort of underlying group, if you draw the picture, you just immediately know it. So there's a way that you can learn about the structure of things that really goes essentially sort of via the visual system and via the pattern finding and the spatial sense and things like that that we already have. Okay. Okay, so I only have a few more minutes. This talk was like probably 4 hours long. So, but I want to tell you one more story. Okay, one more quote here. The scientist does not study nature because it is useful. He studies it because he delights in it, and he delights in it because it is beautiful. If nature were not beautiful, it would not be worth knowing. And if nature were not worth knowing, life would not be worth living. And this is Poincaré. So this next story is really, these are some of my favorite pictures because I think that the beauty in the pictures is really tightly tied to the beauty in the mathematics. I used to argue with my dad about the beauty of fractals and whether that was the same as the beauty of mathematics when I was a kid. And this is a situation where I really feel like they've lined up. Okay, so this is a story that I want to start by talking about continued fractions. And to understand continued fractions, you can understand it in a beautifully visual way. And the start of that story is just to organize the rational numbers into in some sort of way. You think of the rational numbers as living inside the real line, but there's no visuals there. There's no illustration. There's nothing to see what's happening. And the trick is to organize them. So, so in between 0/1 and 1/1, you can put a half, the median, where you add numerator and you add denominator separately. And then you can keep going like this. And it helps to add this extra dimension on the real line so that you have some way of tracking the organization of what's happening inside that real line, which is too low dimensional for you to see anything, right? And so if you keep doing this, you get this beautiful tessellation sitting above the real line. And then you can describe what a continued fraction is, not as some sort of symbolic thing, but as sort of an addressing system. You take a path from the sky dropping down to the real number that you are interested in, and you have to sort of pierce through all of these bubbles in this froth, this fairy froth of bubbles. And as you track your progress, you could label it, I'm going into the, I enter a bubble and I move into the left bubble from there, and then I enter that next bubble and move into the right bubble from there, and so on. And it turns out that that is essentially the continued fraction expansion. So I think that adding this extra dimension onto the real line gives you some way to think about the rational numbers in a visual way. And so this is a picture from Carolyn Seary's paper, which I highly recommend, where she draws this pattern. And inspired by this, I think perhaps, Asmus Schmidt was interested in whether you can do the same things, do continued fractions for complex numbers. And he wrote a paper about this in which he drew this diagram here. And this is all that he drew. This was sort of one level of the subdivision in some way. So he figured out that you had to subdivide the plane in a similar way to the way those bubbles are sort of, you break it up into you label a bubble, and then the bubble has sub bubbles, and then those bubbles have sub bubbles, and so on, right? So it's like this repeated dividing process, subdivision process. And so these are pictures of like what you do at one stage. But he didn't draw, this was in 1975, he didn't draw any further than this. I mean, these may well be hand drawn. And so if you actually draw the full picture that you get from what Asmus Schmidt described, this is what it looks like. And it's absolutely beautiful. This is the structure of the Gaussian integers, of the integers in the complex plane, where you can see the integer points are sort of the biggest points that attract your eye, those pencils of circles that connect at one tangency point. And then all of the other rational numbers here that are that lie in the Gaussian rationals, these are all tangency points in this picture. And in order to see this picture, you have to figure out how to draw it, because you have to decide how many circles to include. If you include all of the circles, it'll just become a completely black screen, right? It's completely dense. It completely fills the picture. But so you sort of include them down to a certain dimension. And in this picture, I've given them some structure by coloring the circles according to the residue class of their curvatures, because again, the curvatures are integers. And in fact, you might notice that in fact, this contains the Apollonian circle packing as a subset of these circles. In fact, this picture, if you draw it out, is just the complete picture of, it contains all of the integral Apollonian circle packings that can exist. And so this picture, the actual definition of it is really just an orbit of Mobius transformations whose entries are Gaussian integers, applied to, say, the real line as your starting point. And so it's really a picture. This really is an essential picture of what the Gaussian integers look like. And so as a number theorist, then you ask the question, well, what about other number fields? And you can draw these pictures for other imaginary quadratic number fields. And so, for example, we have root minus 2. And let's see, my slides are very slow. Root minus 7. And root minus 11. And then we start to get, they fall apart. They're no longer connected. And what's amazing about these pictures is that they capture the mathematics. All of the important things that you would want to know about a number field are somehow visible in these pictures. So for example, whether or not the picture is tangency connected has to do with whether or not the ring of integers is Euclidean. All of those points there are the actual points in the field. The circles themselves, here's one where they're not connected. The circles themselves actually correspond to ideal classes. So all of the things that number theorists spend all of their time talking about, and the first things you introduce in an algebraic number theory course, they actually have an incarnation in the picture. And so that's what I find so fascinating about these pictures. And so maybe I'll just, I should probably stop around here and just give a couple of last thoughts about this experience. So what happened was, you know, I got interested in these Apollonian circle classes. I saw that they had lattices, and it turned out that those lattices were the ideal classes. And I discovered Schmidt's work and started drawing the pictures. And then as I drew the pictures just asked the questions, right? So the pictures, some of them were connected and some of them were disconnected. So you ask, why are they connected or disconnected? What are the tangency points? What do the circles represent? What does it mean when a chain of circles gets bigger and smaller, or, you know, that two different circles are connected in a component? And I was actually like printing these out. I was just graphing tons of these, printing these out on paper. And I actually had like a ruler to try to measure the different ones, to try to figure out what the symmetry group that was going on in the picture was. And it was a research process, which just felt like, I don't know, it's this beautiful synergy between the beauty of the mathematics actually is sort of the beauty of the picture in this case. It's so closely tied. Okay. So here's the class group. This one has class group 2. So there's actually sort of two components that can nest beautifully with each other. And I probably have a quote here to end with. Beauty is truth and truth beauty. And I only got through half of my slides. Thank you.
Thank you so much. There are folks posting on the Discord, but I wanted to ask one of the questions from Steven Stadnicki on the Q&A, which was that these imaginary quadratic field pictures are amazing. Have you looked at the same for cyclotomic fields?
Yeah, so this is a really interesting question. You can't sort of do naively the same kind of picture, because what's special about the imaginary quadratic fields is that if you take the ring of integers, they sit discretely inside the complex plane. And so if you want to do something analogous, you have to use, for the number theorists out there, you have to use the canonical embedding, Minkowski embedding, into some real vector space, which would be higher dimensional. And especially if you're looking at the cyclotomic family, as the degree of the family is increasing, you're really going to, like, I don't know how to draw it. That's one of the things that's so frustrating about our brains, is that they're so well designed for 2 and 3 dimensions and so incredibly poorly designed for more. I haven't tried even in the lower dimensions to do some of these other pictures, but I was just tempted recently after a research visit to try real quadratic fields, because there at least you would still have dimension 2.
Awesome. There are other questions. There's things going on in the Discord. There was a call for you to give at least 4 more talks in this seminar.
Well, there's the
Which
second half of this one. I can put my
I
slides on my website.
I thought it was beautiful. I have a question, which is poorly formed, but it seems like you've sort of you've stumbled upon an interesting use of quadratic reciprocity in seeing pictures here. You're looking at class groups and seeing in pictures, and my sort of like progression through number theory says, okay, where's the class field theory? Like, could that be the next obstacle for some of these integers arising in the circle packings, or is that something you can sort of see, at least for imaginary quadratic fields, in these kinds of pictures here, or is that sort of
That's a wonderful question. So I think one of the things which one of the lessons that I was thinking about when I'm preparing this talk is the way in which working visually allows you to use so many different types of creativity. Because I think all of the important big moments in mathematics research, they come from these creative insights of one kind or another. And the more tools that we use, I had a quote later in my slides from Poincaré on this, the more tools that we use, the more opportunities we have. And so the kind of creativity that working visually brings is really powerful, I think. And so the question sometimes is like, how I'm interested in some particular mathematical thing. How can I make it visual in some way? And then it will tell the story. It'll tell you what questions to ask. It'll tell you what, has to be true. But the question is sort of these things which we traditionally think of, particularly in number theory, as not being particularly visual. For me, number theory is always kind of visual, but I think it's usually very symbolic. And so the really challenging question is just to figure out how to capture those things. And I don't know the answer, because like this is something, these Schmidt arrangements are something which I just totally stumbled upon. It's not like I went out seeking to figure out how to visualize the class group, for example.
Right.
Yeah, so it's a mystery, I think.
Sure.
A good mystery.
I wanted to just keep on going through the Q&A. I know it's after 1, so if you have to leave or if folks have to leave, that's totally fine. But I think there's some great questions, and unless Aaron disagrees, maybe it's worth going through. I think the first asks just if there's a paper associated to this abelian sand pile, Apollonian circle packing, and lattice connection.
Yes, and I could put, what I'll do is so I have to go teach after this, so I might not be able to do it in the next hour, but after that I can put a link to the several papers which are related to that.
Cool. Yeah. So maybe keep a lookout for that in Kate's thread in the Discord. And then the fourth question that appeared on this Q&A was, thank you very much for the talk and awesome images. Could visual intuition be an innovative way to teach and inspire mathematics to non-mathematicians? That's from Diogo Enriquez.
Oh yeah, absolutely. I'm 100% on board with that. I enjoy giving talks like for the undergrads, and in teaching in my classes, I try to do as much visual interpretation of things as I can. And it's such a fun exercise, right? Like you have some algorithm for factoring, say, because I was teaching cryptography last semester, and you're trying to figure out how to convey what the algorithm is doing in some visual way. And so you end up with some robots who are moving around on the screen doing, accomplishing something. Maybe they're just dots actually, but yeah, I think that trying to figure out, and again, I did half my talk, but there was like a fourth section somewhere where I was going to talk about some of the attempts. I've been focusing on integer sequences and how to figure out how to capture aspects of integer sequences. So like, we're often, as number theorists, very interested in what is the factorization of the numbers in the sequence. Like I was talking about the Apollonian data, where if you write it as decimal numbers, you can't tell that those were all 18 times the square. And in this sort of restricted situation of integer sequences, I've been trying to figure out, okay, here's a property I might be interested in. How could I visualize it? And I think that's a really fascinating exercise, because you have to match the mathematics to the various things that your brain is good at doing. It's good at noticing symmetry. It's good at understanding 3 dimensions from 2. It's good at, all these various things that your visual system can do, and so on. And you have to try to think about, the use of color. And I think it's a really fascinating thing to try to do. And so even just trying to do that, never mind succeeding in teaching students, is extremely valuable, but I'm a total amateur at that.
Awesome. I think that's a great answer. There's more questions on the Discord. There's connections being made to other things like Henry Sigerman's cohomology fractals and arrangements looking like projections of Z3. But maybe I'll say let's keep chatting on the Discord. I think there's so much to talk about. And thank you one more time for your talk, and hand the floor over to Aaron one last time to close us out.
All right, thank you. And thanks to all the presenters for the beautiful talks. We do have to wrap up so Kate can go teach. Thank you all for coming. Hope to see you again next month. And once again, remember that if you would like to give a show and ask presentation, please sign up to do that. Okay, thanks everybody.